Oh my gosh, I'm getting tired. Third take on this one. First time my board froze, couldn't get it fixed. Second time, my battery ran out and didn't save any part of the video that I was already making, so take 3. All right, first I would ask you to take out a pencil and your notebooks, but I don't have to. So you could be laying in your bed, you could have a pencil, you could have your notes out, whatever you want to do. And you can go to the bathroom whenever you want. You don't have to ask permission. Okay. So the first thing we would do, obviously, is review layers of the Earth. But nobody's here, but well, that's okay. We'll try it anyways. Travis, what are you doing? What is that in your pocket? Give me that. You know where you're not allowed to eat in the classroom? Oh, wait. You can eat. You can eat a peanut butter sandwich and watch the video at the same time. How cool is that? I do miss you guys. All right. So, which layer is the thickest? Brandon. The mantle. You got it. Preston, which layer is made mostly of basalt? Oceanic crust. You are correct. Which layer is a solid spinning ball made mostly of nickel and iron? Kimberly. Yes, the inner core. You got it. Who thinks they can name the order of the layers? Anyone? Jeremiah? God, even I can't do it. Oceanic crust. Continental crust, oceanic crust, lithosphere, asthenosphere, mantle, outer core, inner core. Good job, Jeremiah, even though that was really mean. I'll still give you a Skittle because you can't eat it anyways. All right, moving on. Continental drift. Whoa, did you feel that? Believe it or not, where we are standing, it's actually moving. The whole ground we're moving on moves about 10 centimeters a year. So that's kind of what our lesson is going to be about. All right, let's do our I can statement. It's just not as fun without you, but I'm still going to do it anyways. I can understand and communicate how the theory of plate tectonics explains the motion of the lithospheric plates. No! Sit down. Not time to go yet. All right, everybody say lithosphere. Say asthenosphere. All right, those are probably 2 of the hardest words to say in this unit. All right, continental drift. First thing we would do is an inquiry activity. I would give you and your partner these puzzle pieces, and I would say, okay, go ahead and put this puzzle together. And you would probably put this together. Am I showing that right? And then you might put these little things together, and then you would maybe put the star together. All right. And I would ask you some questions about how did you decide what pieces went where. A lot of you would say the shape. Some of you might say the color. Some of you might say the designs that were there, like you put the lines with the lines, you put the star with the star. That's exactly how they came up with the theory of continental drift. So after we did that, then we would actually do the same activity with these puzzle pieces. So you and your partner would have the puzzle pieces. Whoops, I dropped Australia. And you would try to put them together according to shape and according to some of the things that were found across, or the similar on both continents. So I don't know exactly what I'm pointing at, but some of it would be vegetation, so the same type of plants. Some of it would be the same fossil, like the same dinosaur bone fossils, and then some of it was also similar rock layers, so they would find kind of the same type of rocks. Now, of course, these are now apart, so they were thinking, the idea is at one time they were joined, and that's how those similarities got on both continents. So we put that together, we talk about that and discuss that a little bit. Then I would hand you your notes, and you probably don't want to take notes while the video's playing because I'm going kind of quick. But this whole presentation is going to be in this assignment for you to just kind of take notes at your own pace. So believe it or not, this is sort of looking like the eggshell of the Earth. We can't see them because a lot of the cracks are under the oceans, but there's actually, the whole Earth has cracks in it. And these are the actual plates. So no, these are not the continents. These are kind of like the cracks where these are happening like underground. These are where the different plates are moving. Oh, love this video.
The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental landmasses, the thinner of the two plates bends and slides under the other. As the edge of the sea floor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
All right, so hopefully that gave you a little more insight as to what's happening below our feet. All right, this we've already kind of talked about, the difference between the continental and oceanic crust. This one is just explaining the thickness and kind of the density. So when we start talking about like some plates kind of going below other plates, the ones that are more dense are always going to go underneath. The ones that are less dense are always going to sort of ride over the top. And I think there was a density activity, I think in the chapter before we're doing this one. So this is the oceanic crust. You can see it's much thinner and it's made of basalt. Basalt is less dense than granite. Here is just another picture of sort of what's happening, and this would be where there's a little bit of subduction. So these might be two plates sort of moving together. Oops. Here is sort of talking about the difference between the lithosphere. This is sort of where we are. This is kind of like the crust. And then the asthenosphere is where the mantle starts to kind of turn into silly putty. And remember, those convection currents are what kind of are pushing the plates around. All right, now we come to the guy who sort of like came up with this theory. And the cool part is he was a meteorologist. He did not study geology. And he sort of came up with this theory accidentally when he was kind of like up in the air and kind of like looking down on the earth. So Alfred Wegener is the one who gets credit for coming up with this theory. Unfortunately, he died before like his theory ever became accepted. And this video, it's kind of cute. And I think you're really gonna find the ending somewhat strange because he did die, and you're going to see what they kind of did with his body after he died.
hardly anyone in the early 20th century said, why are there oceans and why are there continents? Wegener is a wonderful example of how science benefits from people coming from outside a scientific field and saying, well, why don't you look at it this way? Getting into a balloon and going up into the air for a meteorologist is like getting into a boat and going out on the ocean for an oceanographer.
He goes up in a balloon because he wants to take measurements of the atmosphere. He's not the Wizard of Oz. He's a scientist doing science.
Wegener flew as much and as often as he could. He wants to write the best book on the physics of the atmosphere, and no one had ever studied the atmosphere in the high Arctic before.
This is a time in history when one of the most exciting things you can do as a scientist is to go on an Arctic expedition.
It was adventure travel of a North Pole, South Pole kind. Wegener's out there in the winter night taking these huge box kites and attaching recording instruments to them and then winching them back down to get his instruments back.
Nobody ever said that Arctic exploration was a picnic.
Wegener had to learn how to hunt seals, how to drive a dog sled, how to travel on ice without being swept into open water, how to protect your dogs from polar bears. The travel in Greenland, his time with icebergs,
The way in which the ice floes form jigsaw puzzle pieces.
the way the ice cap splits apart and fissures. All of this was part of his imagination when he made his discovery of continental drift.
I wouldn't really call it a discovery. What he really had was an idea.
He went to his office, and his office mate said, look at this beautiful atlas my parents gave me for Christmas. And he wrote to his fiancée, did you ever notice how South America fits into Africa? Let me pause and say, there isn't a child on earth over the age of 12 who hasn't had the same thought, right? You can see it. What was different about what Wegener saw? There were lines on the map that represented depths under the water, and they're exactly the same shape. That means that this is part of the structure of the Earth. How did that come about? Maybe the continents drifted apart.
It was radical because it was new. The Americans say the continents are fixed. Europeans think they move, but they think they move up and down. And Wegener says you're all wrong. Yes, they move, but they move horizontally, not vertically.
He would write a paper in 1912. He said, I think everybody will really be happy. And of course, everyone wasn't really happy. Everyone became very unhappy.
There was a almost universal rejection of his theories to begin with.
Here's the problem. Scientists are very suspicious of fundamental novelty.
He was regarded as an outsider by the geoscience community because he had no academic credentials in that field, and so he was not considered qualified to make any statements in that field. What he was doing that was so different, though, was drawing together multiple lines of evidence, not just geology, but vegetation and paleontology. The botanical people responded very positively because it explained the distribution of plants and animals over the world.
In different places on Earth, you saw virtually the same fossil records. The stratigraphic columns were extremely similar as well. And Wegener's idea, his big idea, was you could explain all of those things if the continents had moved.
So he would write a book in 1915. People said, well, this is wrong and that's wrong. And then he wrote another book in 1920. He comes up with the name Pangea. And then he wrote another one in 1922. And he kept fixing it and fixing it and fixing it. It's one thing to think of an idea, and it's another thing to work it out for 20 or 30 years.
That book's still available on Amazon.
Continental drift was something he was interested in, but it was never the focus of his scientific life.
The Arctic pulled him back in. He was really too old, almost 50 years old.
He landed there with 98 tons of equipment.
And from the beginning, things didn't go well.
They had many things go wrong.
The base in the middle of the ice cap did not have enough food, and he said, this is my responsibility to resupply.
And he got several sleds together.
It's the worst conditions you can possibly imagine. His companions wanted to give up. And at twilight, Wegener said, let's go for a walk. And he took them out and pointed to the ice and pointed to the sky and said, we're trying to find out how all this works. It doesn't matter whether we live or die. The important thing is that the work go on.
And I guess that's why I love Alfred Wegener, because it's not really about himself. It's that he believes in science, a kind of great metaphorical expedition.
At the end of all this, they were able to supply the station at the middle of the ice. And then they got there, and there wasn't enough food to last the winter for all of them. Wegener said, I'm going to go back to the coast. He didn't like to ride on the dog sled. He liked to ski next to the dogs. He had a heart attack and died. He's still there. The German government wanted to bring him back for a big funeral, and his wife said, no, leave him there. He's where he wants to be.
Creepy. So he's still there. Told you it was going to be a weird ending. All right, so Pangea is the name of the mass before they think the drifting happened. You will see this spelled two different ways. Remember how scientists always argue about things, they can't come up with the right way it should be spelled. So sometimes you'll see it AEA, and then sometimes you'll just see it EA. It means all lands, and this is kind of where he was going. So here are kind of the plates and the volcanic activity before everything started moving. Okay, and you know that they didn't kind of accept his theory at first. Talked about evidence. You do need to know there's three main types of evidence that you need to know about how Wegener came up with his theory, and that is the shape of them, that they fit together like a jigsaw puzzle, because he found similar plant and animal fossils, and because of the rock formations. So they actually, our Appalachian Mountains, kind of are the exact same composition as I think it's the Aleutian Mountains in Europe. So that's another reason that he came up with this theory. Oh, they also had glacial striations. You do not need to know what that is, but I guess they're kind of grooves that are put into the crust, and they noticed that those grooves were similar, meaning that there probably was a glacier that was covering two continents at the same time. Oh, here's the mountain ranges. So here's the Appalachian Mountains, and it's the Caledonian Mountains, and then there's the British Isles. So those used to be all kind of matching at one point. All right, so we're getting to the end. Why do the plates move? They move because there is hot taffy, the mantle's moving, convection currents. They're riding on top of hot flowing rock. They're riding on the lithosphere. The plates move because of convection currents, and the convection currents is the rising of hot material and the sinking of cold material. We've already talked about that. And why can the lithosphere float on the asthenosphere? Because the asthenosphere is fluid. And evidence, you do need to know these three pieces of evidence: similar fossils, similar rock patterns, and matching mountain ranges. And right now we would do a quizzes, so that I kind of understood what you guys, kind of like a little formative assessment, but I'm going to sort of put that into the assignment following this one. All right, I'll see you guys for a little more on plate tectonics next time. Peace out. Oh gosh, I gotta climb up here to turn the video off. Ooh.